So today's exercise is the fifth one, which is the filter design 2. And let's take a quick look at what kind of things we will be doing. First one is design a band stop notch filter, which was basically the last thing I think on the whiteboard. I will download the pictures soon. Okay, but anyways, band stop notch filter with the following properties. So there are the sampling rate given, notch frequency given, bandwidth given. So only thing which you need to do there is to figure out where the zeros and poles are and how they actually match, what kind of system parameters you get out of those. Okay. Then, well, this is just plot zeros and poles. That's kind of verification. But before that, when you will verify your design from amplitude response, and then plot the impulse response, old stuff. Okay, that's the first part. The second part, designing an IIR low-pass filter and verifying that you could do the design. And basically, next one is to transform the filter to bandpass filter. I will show you some tools to do that kind of things. You don't need to do everything by hand anymore. Then design an IIR high pass filter. Okay, parameters given. Then the seventh one. On the previous exercise, deadline is today at some point at the end of today. On FIR, you are actually defining these parameters, filter requirements, filter requirements on exercise 4.7. And basically now you take those filter requirements and try to find a matching the IIR filter design. And basically you did the same thing already on 4.8. You did the design. Now you basically just compare those filter designs. Amplitude responses, how they actually differ. There are some differences. Just describe how they differ. Then phase response. I would expect something like linear, nonlinear phase response. Then order number. I haven't emphasized that one too much, but the order number is the highest delay on the system. It's the same as order number. And why it's called order number is because of the polynomial of z. What is the highest polynomial number on those rational polynomial of z of the transfer function? Okay. Okay, and then ninth is quite fun, since actually that will be some sort of, say, design which also could be continued as the implementation on an embedded system. So designing a filter or filter bank, 3 bands, low, middle, and high frequencies with certain properties, and verifying that one. And then how to basically make that that one to function. Okay, good. First, some hints on the how to do the band stop notch filter. exercise 5, and first one there is band stop notch filter design. And let's start with the sampling rate. I had that 2 kilo samples per second. Let me take a quick look at that. I don't have exactly the same here. No, I don't. Good. So sampling rate of 2000. That was what I had example on that lower right corner there. So that's sampling rate. Then corner frequency, or center frequency for that notch. So where does it actually take the and has the best attenuation? At 100 Hertz. Typical for, or from the transformers, you usually get the 100 Hertz signal is the highest or the most energy on this this line noise, AC line noise, because of the rectifier. Okay, 100 Hertz. Line humming. Okay. So, and next we also had the minus 3 dB point, which is the half width of the filter, delta F, dF. That was 50 Hertz on the previous exercise there, or example. So that's the half width of the filter, meaning, okay, remember this one. Oops, oh. Not like that. We have the 0 point at the angle, and then we have pole, and the minus 3 dB point, F minus 3 dB, is actually at the angle here. If this is A and that one is A, minus 3 dB point is right there. Where this range here is 1 minus A. All right, so minus 3 dB point on both sides. So that's the plus and that's the minus, which means that the full width would be, well, that plus that. Okay, so half width of filter. Next, we'll place the zeros. Exp J and complex conjugate minus J. Okay, I'll make this one already a column vector, n times 2, or actually 2 times 1 vector. To say MATLAB, okay, this is a zeros and poles we are talking about. Then I need a angle here. The cutoff frequency angle is at, oops, at this angle. So FC over sampling rate, that basically is just the ratio of those, which would equal 2 pi in the angular frequency. So that's where the zeros are. Okay, let's first play that, okay, our poles are actually on the origin. This is just, curiosity case. If we had poles on origin, then the zeros and poles, let me take a quick look if I place those ones correctly. Okay. Sorry, not 0, 1, 1. 0, 0. Of course. Poles at origin. That's why I always, plot the 0 pole planes, and that's the circle there is the angle where the this 100 hertz is. That angle tells where the 100 hertz is on this Z plane. Good. And corresponding filter coefficients or parameters, same thing. BB is the polynomial defined by zeros. We used that one already on one of the exercises, but anyway, so BK equals the polynomial coefficients of polynomial defined by those roots. Zeros actually, yeah, zeros there. Okay, same thing for A parameters, but that's for poles. There we go. Now we have A and B. Let's see, A equals 1, 0, 0. Okay, so it's FIR system. Our poles are at the origin. Good. B, okay, those are the filter coefficients. All right, and those are easy coefficients. Since there is only a, one value that difference from 0. Oh, 1. And then we can actually calculate frequency response of BA, for example, 1024 points, and sample rate. Not, okay, there. There we go. So that's basically what we get for the filter design. 100 hertz is the notch frequency. However, this has a problem that also this distorts badly the amplitude response. So now we will add the pole close to the that unit circle at distance of delta F to basically define this bandwidth of that notch filter. Okay, move poles near to unit circle. Okay, the radius for that one is 1 minus A, and A here. That's a bad. Okay, that's the A3 dB equals. Now we have the delta F was df divided by sampling rate times 2 times pi. Okay, so that's the corresponding angular frequency. So that's delta omega. Okay, and now that's how far we need to get. Oops. Let's see how much is the delta omega. So it's 0.15. Now the radius of the pole is 1 minus A3 dB. Okay, radius of poles. And they are on the same angle as the as zeros. So I would guess this would do the trick. zeros per empty unit circle. We just multiply with a real number. What you get is basically the number which has the same angle but different radius. Okay. And now zero pole plot looks like that. Multiply that a little bit there. So basically, if I make here a line just for fun from 0, 0 to 0, 0 to real of Z1 maybe. Imaginary of C1 that should go. Oh, I got it. Yeah, I did something wrong here. But anyways, forget that one. I tried to do a line here, but it didn't quite work. Well, I tried to make a line. Ah, yeah, of course. 0 real of CZ1. There, now 0. That'll work a little bit better. Yep. So the 0 and pole are on the same angle, at the same angle. Good. Then I'll do the same thing as previous. So BB is polynomial that. Well, we didn't change the zeros, so that'll be still the same. We changed the poles. No, poles. Oops. We changed the poles. So we calculate the denominator polynomial again, which looks like that. Okay, so we need to do some calculus here. Those are the feedback terms, not anymore FR system, and just Z-plane of, not Z-plane, but but frequency response. Okay, there we go. So we designed a notch filter, and with, let's take a closer look. -3 dB point is roughly here, so it is roughly at 50 Hertz. Another -3 dB point is roughly here, so it's also 50 Hertz from the center. So the full bandwidth is 100 Hertz, and the half bandwidth is 50 Hertz. Well, that's the design. And system parameters, we know BB like that, A like that, and we can now use those in a filter and get rid of that 100 Hertz noise. Good. Next part. It's about IIR filters. And there we basically use more or less 3 different filter designs here. One is Butterworth, another is elliptic, and third one is the Chebyshev one. Let me take a documentation of Butterworth, doc butter. Okay, returns the transfer function coefficients of an nth order low pass digital Butterworth filter with normalized cutoff frequency Wn. Okay, normalized. Here the normalization is not from 0 to pi, but 0 to 1. And yes, you can also define the high pass or band pass filters. by just giving it enough of parameters. And yes, there are some examples. Okay, so this gives the filter coefficients. So let's see, BB1 AA1 equals Butterworth, and how to use it. Nth order, let's take for example fourth order, then normalized frequency from 0 to 1. Let's take a cutoff frequency on this 2 kilohertz system so that it would be 200 hertz. So the normalized frequency is 200 divided by Nyquist rate, which is Fs divided by 2. Okay, and those are the values. Fourth order, meaning you have 5 parameters both in B and A. And the frequency response, BB1, A1, 1024 points, sampling rate. So I said it's 200 hertz cutoff frequency. Yes, it has a 200 hertz cutoff frequency. The this amplitude response goes to, you know, haywire here, but anyways, up to say 100 dB. That's what the frequency response looks like. And there's also the phase response. Well, IIR filters always have nonlinear phase response. But we can play with also with the other filters, say okay, Chebyshev 1. Do we have the function hints? Oops. Need to find it first. Ah. Ah, okay. Document as Chebyshev 1. Okay. Here we have about the same parameters, but we also define the passband ripple. Let's keep the same order number. Then the second parameter was the passband ripple in decibels, 2 dB, and the cutoff frequency same way. Okay, and again we have just, you know, parameters like that, and well, frequency response. Oops. A little bit different. Okay, there we go. I cannot quite see the ripple. Okay, there we go. So on passband it has 2 decibel ripple. So variation of the bandpass response. Compared to this previous, this has actually a better transition bandwidth. Okay, you cannot really see it from here, but it has. All right, and then the third filter example is the elliptic. Yes, elliptic filter design, which also you define the stop band attenuation there. All right. 3, and then bandpass ripple is still the same, and for example 80 dB on stop band attenuation, still the same cutoff frequency. Yeah, those are the parameters. There we go. Looks like that. So it has also, it has steeper transition bandwidth since it also uses utilizes the zeros of the system. Okay, this part, the passband part is more or less the same as in the case of Chebyshev. But the stop band is basically using the those zeros. Good. How to actually find the correct kind of, since there's not too much of things that you can change here. The only thing what you can practically change in this design, well, the passband ripple is usually defined by the application, how much you can tolerate that one. Okay, another one is also how much you must have stop band attenuation. Then again, application dependent. What is your cut-off frequency? So how to fix now the transition bandwidth, so where the stop band begins. You can actually change only one parameter, is the order number. Okay, just add calculations. So now we have 8th order system, more calculations, but we also got much steeper transition bandwidth. All right, there we go. Let me take another figure here so you can see. So these two systems have, the only difference here is the order number. Maybe I should actually zoom into a little bit. Yeah, okay, now they are more or less on the same axis. Okay, same ripple on passband, but because we have more also the zeros here, then we get the transition bandwidth also narrower. And okay, a lot narrower. So here the transition bandwidth is about from 200 Hertz to 550 Hertz also. So it's 350 Hertz transition bandwidth, doubling the amount of poles there and zeros. That 350 is now about 35 or 40. So factor of 10 improvement on transition bandwidth. Okay. How to define the order number? One way is actually to just play around, test it. There's also all of these functions: butter, Chebyshev 1, and this elip has also elip n. Okay, order number. Order number big N equals butter ord. I think that was the let me take a quick look at the help. Elliptic, 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 yada yada yada. See also ellip ord. Okay. For elliptic filter design, there is also ellip ord, which tells you basically calculates the minimum order of a digital, well, or analog elliptic filter required to meet the set of filter design specifications. All right, so we have passband frequency, then you have stop frequency, passband ripple, stop band attenuation, and this calculates the order number. So, okay, same thing for Butterworth filter, I think. Help on selection. Oh, no, it has different name, I think. Let's see. Buttord, okay. Of course, they must be, you know. Naming convention is not, you know, they are made by any programmer. Looks more like a physicist or mathematician. Okay, Buttord. Buttord, how to use Buttord? Who? Buttord, it requires, okay, fundamentally the same parameters. So Buttord, guys, Buttord, just give it a 1. Well, whatever that WN is. Buttord band pass, for example, if that was the 200 Hertz, 200 divided by fs over 2, normalized to 0 to 1. Okay, stop band starting, for example, at 400 Hertz divided by fs over 2. Oops. Then next is the passband ripple. Butterworth actually has 0. But it doesn't actually matter. I'll just mark it 3 here. 3 dB. Maybe it uses it to calculate that one as a 3 dB point. Okay. And then stop band attenuation, for example, at 80 dB. Okay. Order number 12, order filter. And let's see, WN was scalar corresponding cutoff frequencies is also returned. Okay. So now we can use the BB1, but instead of that we put NN and also WN here. So that'll calculate the 12 order Butterworth filter coefficients. And frequency response of that one is something like that. So our design was to have the 3 dB point at 200 Hertz. Yep, I believe that one. Then it has the 400 Hertz at 80 dB at 400 Hertz. Yep, looks like it's correct. So at 80 Hertz we have attenuation of, and 400 Hertz we have attenuation of 80 dB. Okay. Same way we can calculate also the other ones. So say JB1 order, I think that's the, let's see. Let's go to Chebyshev 1. And where's the, which function gives the, no, it doesn't. Ah, this is the, okay, I took wrong one. Which function gives the Chebyshev 1 or Cheb1 odd. Okay. Naming convention is really funny here. Same parameters. Although now this is 2 dB. So cutoff frequency, stop and start frequency, and then the okay. So in order to achieve the same stop band attenuation, especially stop band attenuation, we need only 8th order Chebyshev filter compared to 12th order on Butterworth. I could also show the frequency response on, but I'm going just forward on elliptic. Remember, now we are combining basically the ripple on passband with the some zeros on the stop band. So we basically improve the previous Chebyshev by moving those zeros from that one single location and distribute those. 6th order. So choosing the correct kind of IIR design, basically you can cut the amount of calculations down by a factor of 2 at least. Okay. Mm-hmm. 6th order. That'll do. Right. Three. There. Okay, good. How to transfer this one to bandpass filter? I think we can do it by low pass to bandpass. Transforms low pass analog filters to, oh, that's analog filters. I thought it was, let's see. Yeah, these work only on analog filters. Okay. And we are not going to use those more sophisticated tools. Forget, let me do something about that exercise. There, done. You don't need to do the exercise 5.5. There is a transformation method, but it wasn't the one that I thought about. Okay, sometimes that one happens. And let's see, but the low pass, well, let's see. Let me take a quick look on the exercise now. High pass you can actually design with those tools. One way of designing the high pass filter, if you have a low pass filter design, then you just swap the frequency axis. But you can also apply those design tools, Butterworth. For example, Butterworth with the filter type. Okay, you can filter stop band or use the stop band. You can actually make the high pass filter. There. So let's see. Just for example. So PB H, like high pass. Same cutoff frequency, but high pass. There. those are the filter coefficients, and basically that's the Butterworth filter with 200 Hz cutoff frequency. Okay, simple. It's just use these functions. Simple functions that give you the parameters. Then let's see, that's more about design, and let's see that one. Then, okay, that's also filter design. Okay, this I need to explain a little bit. How many of you are familiar with the, say, audio equalizers, other than our grandmaster of recording there? Okay. This is basically some fundamentals from media engineering or media, let's see, media in any ways. The audio signal. Okay. Humans are analog. That's a surprise, right? We are not digital, we are analog. Our senses are analog, and more or less, our senses are also more or less logarithmic. That's why we describe the voice pressure actually in decibels, and that's why also we are more or less having logarithmic scale also on the frequency scale. On digital world, it's easier to plot linear frequency scale, but on analog electronics, you plot all of these frequency responses on logarithmic frequency scale because, well, that's basically how human interprets the frequencies. 1 octave. Let's take piano. That's octave. Octave. Another one here. Let's see. Let's put the black keys there first, then I can figure out where the white ones are. Okay, black keys go something like that. Black keys, and that actually those are also dividers for the white ones. There. Those are the keys. There are 12 half notes. That's C. That's the second next C there. What octave higher? Well, if we have, say, frequency Fc here, next octave frequency is 2 times Fc. And the next here starts at C again. That's 2 times that one, so it's 4 times C. Next one will be 8 times C, 16, so on. How about the half notes then? Actually, there are 12 half notes. So if you want to get a note, for example, here, what you need to do is start from some basic note. Well, usually you start with A. Okay, you calculate how many half notes. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. 11, 12, 13, 14, 15, 16, 17 half notes after that. So that frequency would be Fc times 2 to the power of 17 divided by 12. Okay, if you plot it basically on linear scale, you would have, you know, quite little information there. So to get the information correctly there on the frequencies plot, you actually have this one also logarithmic. Okay, how about, what is the lowest frequency you can hear, roughly? Twenty hertz. Yes, 20 hertz. What is the highest frequency you can hear, roughly? 20 kilo. Yes. The logarithmic scale would be 200, 2K, 20K. Right. The low band. That's the low. The high band. That's the high band. That's the middle band. Okay, so that's why we have these cutoff frequencies there, 200 hertz and 2 kilohertz. Now, basically, human ear kind of recognizes these as same frequency space, or the same frequency kind of blocks. Now you can roughly tune the highest notes compared to the lower notes. Okay, which means that you need to put the low pass filter cutoff frequency right here. Wow, I can do it also with this one, not only on the whiteboard. High, let's see, high energy, blue. High pass cutoff frequency would be there. And the middle, it has two cutoff frequencies here and there. On an analog scale, it would look like that. Okay, which means that these transition bandwidths, they are not the same for all the transitions. So that's basically if we have transition bandwidth here, something, we have that 10 times here. Just because it feels like the same. 10 times? Yeah, 10 times. Yeah. And if we have the, well, the same here, 10 times the transition bandwidth original. And this one here is actually the original transition bandwidth, which gives you some ideas of how to do the filter parameters for those filter banks. Okay, and now those are just the filter banks. The system, how does it work? Okay, we have one signal in, then you have 3 filters, with separate gain, and then summing the output. High, middle, and low. Okay, and you need to then, in order those to do anything for the signal, the only thing what you need to do is just put some adjustable gain for the signals. Yeah, just a scaling factor that you will scale the signal before you sum it. Okay, same here. Fundamentally, you don't need the middle frequencies at all. So have you ever thought about why on car stereos only bass and treble? Okay, you don't need that since you can scale the whole darn thing, you know, just putting a, for example, amplifier here, and you know, it's the full volume, the adjustment there. Okay, that looks like a working system. Your thing is here basically that you will design those filters, filter coefficients, show the amplitude responses. And after that, the 10th is you will apply those filters exactly like that. So you will filter the input with some high pass filter, middle pass filter or band pass filter, and low pass filter, and adjust the gains. So on this one, it's I've made it simple. So bass, which means the low band, is plus 10 dB, and the high pass, actually it's 6 dB. Yep, plus 6 dB. Whoops. I see. I made a kind of. Let's match the colors. There. So filter those separately, add some gain, meaning multiply with the scale, and combine each of those output signals. That's your output. And then you can basically also listen to the original and the filtered one, if you please, but I'm more interested about the that you can do the commands here. Okay, any questions about the 5th exercise? If not, then start working. I will download everything what I have done here to internet, including the recording. Okay, thank you. Over and out.